and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 10, Lesson 2 on the volume of right rectangular prisms. So we looked at right rectangular prisms along with pyramids in the last lesson. Today we're going to talk about how we find the volume. And we want to make sure right from the get-go that we all feel comfortable about what volume even is. So let's start by discussing that a bit. Volume is simply the measurement of three-dimensional space that lies within a solid, right? It's often measured by the number of unit cubes that fit within it. Now this is very similar to the idea of measuring two-dimensional area by using the number of unit squares that fit inside, right? When we say that the area of that is 25 square inches, right? We're talking about squares that are 1 inch by 1 inch and 25 of them fitting inside. Well, with volume, we do the same thing, except we're trying to figure out how many unit cubes fit inside. So let's begin in exercise 1 by remembering how exactly we do that. A rectangular solid is shown below that has a layer of unit cubes in them that have edge lengths that measure 1 centimeter each. An enlarged picture of one such cube is shown. Letter A, what is the volume of the small unit cube? All right, so just a few things. All of these cubes that you see down here are really one of these. I've just taken one of them and kind of blown it up. So as we say, it's not to scale. This is, supposed to be the same size as one of these little guys down in here. Now, let's talk about what the volume of this thing is, because it's important, right? What we're going to say is the volume of this particular cube is 1 cubic centimeter. All right, so literally, it's just what we call it, 1 cubic centimeter. And because we're kind of lazy and we don't really want to write it out like that every time, what we'll oftentimes do is put down 1 cm with a little 3 exponent. You'll even hear teachers call it 1 centimeter cubed. Now, I'm not going to claim that that's wrong, but I do think it's better to call it 1 cubic centimeter because it truly is that, right? A centimeter is a length, just a straight line or even a curved line that has a length of 1 centimeter. 1 square centimeter is literally a square that is 1 centimeter by 1 centimeter by 1 centimeter by 1 centimeter. And then 1 cubic centimeter is literally a cube, right? A right rectangular solid whose faces are all squares. It is a cube that is 1 centimeter wide, 1 centimeter long, and 1 centimeter tall, right? A cubic centimeter that we'll oftentimes abbreviate with cm raised to the 3rd power. All right, simple enough. Now, to find the volume of this, we want to figure out how many of these things fit inside of it. So let's take a look at letter B. How many unit cubes lie in the single layer of the solid shown above? How did you determine this? All right, so in other words, I don't want you to worry about the volume within this right rectangular prism. I just want you to tell me how many cubes are sitting in this first layer. Pause the video now and see if you can figure that out. Well, I'm very much hoping you said 40 of them, right? And this isn't about volume or area or anything like that. This is just about multiplication, right? I've got 5 of them right here, and then I've got 8 rows of 5. Or I've got 8 of them right here, and then I've got 5 rows of that 8. One way or another, right, this is just pure straight up multiplication, right? I've got 5 times 8, I've got 40, right? And again, it's as simple as the fact that I've got a row of 5 and then 8 of those rows, or I've got a row of 8 and 5 of those rows of 8. Either way, it's either 5 times 8 or 8 times 5. Multiplication is commutative, so there's 40 of them. Now, very important, letter C. Your answer in B corresponds to what measurement of the rectangular base of this solid? All right, in other words, that 40 actually represents something about this rectangular base. Remember, we've got the bases right on the top and the bottom, and then we've got the lateral faces that go around the solid. What does this 40, which we can't see anymore, what does this 40 represent about that base rectangle? Pause the video now and think about this. Well, it represents its area, right? We know that the area of a rectangle is length times width or base times height or whatever. But, right, the area of that rectangle, that is 5 centimeters this way and 8 centimeters that way, would be 5 times 8, right? So that 40 actually represents the area in square centimeters of the base. Right, that kind of makes sense. You know, we're really kind of counting how many squares we could lie down on the bottom of that figure, on the bottom of that solid. Now, letter D. How many of these unit cubes will fill the entire solid? And here I've got the picture again so that we can see it down here. So I know that there are 40 that sit on this initial layer because that's 5 times 8. The question is, how many fill up the entire figure, given that the entire figure is 6 centimeters tall? Think about that for a minute. Well, if I've got 40 down on this lower base, think about taking another one of those and stacking it on top, stacking it on top, stacking it on top, etc., right? We would be able to get 1 layer, 2 layers, 3 layers, 4 layers, 5 layers, 6 layers, right? We'd have 6 layers of those 40 cubes. So we'd have 40 times 6, and there'd be 240 cubes that fit inside of there, right? Because we'd have 6 layers of 40 cubes, right? 6 layers of 40 cubes because we have 40 sitting in the bottom layer and 6 of those layers. So letter E, what is the volume of the solid? Use appropriate units. Well, we already have it, right? Because volume literally is how many unit cubes fit inside of a solid. There are 240 of these unit cubes that sit inside of the solid, so therefore the volume is 240 cubic centimeters, or if you want to write it a little bit shorter, 240 centimeters with that little exponent of 3. So 240 cubic centimeters. That's it. All right. So let's keep going. Now, this brings us to an amazingly important formula, okay? The volume of a right rectangular prism, aka the box, all right? So if L, W, and H represent the length, the width, and the height, you know, the width, the length, and then the height of the box, then the volume is length times width times height. And that's exactly what we did last time, right? Remember, last time in the last problem, we took the length and the width of the box, that was 5 and 8 respectively, and we multiplied them together, and that told us we had 40 cubes sitting in the bottom layer. The height literally told us how many of those layers we had. So in the last exercise, right, we had 40 cubes on the bottom layer, 5 times 8. Then we had 6 layers of those cubes because it was 6 centimeters high, so we had 6 times 40, or 240 cubic centimeters that fit into the box. All right, let's take a look at exercise number 2. The volume formula for a right rectangular solid is given by V equals length times width times height, as given on the previous page, or as given right above. Sometimes this formula is given as V equals capital B times H, where capital B represents the area of the base, which is shaded in the picture. Why are these two formulas the same? Well, we kind of took a look at this in the last exercise, but let's just talk about it now, right? So, you know, very often you will think about the formula for the volume of a right rectangular solid as length times width times height, and that's great. But sometimes you'll actually be given you the formula in this form, right? Which basically says, hey, calculate the area of the base and then multiply it by the height. And keep in mind, that's what we did in the last exercise. When we did 5 times 8 and we got 40, that did represent the number of cubes sitting right on the base. but it also represented the area of the base. So these two formulas are the same because literally the area of the base is length times width. So if the volume equals length times width times height, then we can just replace the length and the width with the area of the base. All right? And this is a more generalized formula. Now, for us, we're only going to deal with volumes of right rectangular prisms. Right rectangular prisms. So we are only calculating volumes of boxes, essentially, in Math 6. But by the time you get to Math 7, okay, those bases could be something other than rectangles. They could be triangles, they could be pentagons, they could be anything. And at that point, you really have to calculate the area of the base and then multiply it by the height. And it'll still give you the right answer because the area of the base will tell you how many cubes can sit on the base, and then the height will tell you how many layers of those cubes you have. All right? Never forget that this formula actually has a meaning. It's not just, hey, multiply a bunch of numbers together and get something, right? The first two numbers that you multiply, the length times the width, that tells you how many cubes sit on the base, and then the height tells you how many layers of cubes you have. So, let's keep doing this and move on to a problem that's a little bit more messy, let's say. All right, exercise number 3. The right rectangular prism shown below has edge lengths that include fractions. Letter A, change each of the solid's edge lengths into improper fractions. So you can already probably imagine what's going to happen. I want to know what the volume of this box is. And if this was 1 inch, 2 inches, and 2 inches, it would be actually pretty darn easy. But at the 6th grade level, because you've done a lot of work with fractions and multiplying fractions and simplifying fractions, et cetera, right, we can now be expected to find the volume of a box like this that has fractional side lengths. But especially when they're in mixed number form like this, it's easiest to find the volume if we first turn all of those fractions into improper fractions, not mixed numbers. So pause the video now and change each one of these things into an improper fraction. All right, well, 1.5 inches, that ends up being 3/2 inches. 2 1/3 inches, that is 7/3 inches. And 2 4/5, that is 14/5 inches. All right. So we've got all of our lengths now, but they're in these kind of just fractional forms. Now, letter B. Find the volume of this solid. Show your work. Express your final answer as a mixed number with appropriate units. All right. Well, let's just use the length times width times height. Okay? So to do that, right, we're going to take our 7/3, hopefully. We're going to take our 7/3. We're going to multiply it by our 14/5, and we're going to multiply it by our 3/2. Okay? What I'd like you to do now is I'd like you to try to carry out this multiplication. Let me give you a hint. Do some cross-canceling. It's going to make your life easier. And then I want the final answer in simplest form as a mixed number and with the right units. Pause the video now and see if you can get through that. All right, well, let's do some cross-canceling. It always makes your life easier if it is actually present, and it is in this case. A 3 cancels a 3, leaving us with a 1 and a 1. All right. We also have a 2 canceling into a 14, leaving me a 7 and a 1. And that's all the cross-canceling I can actually do. Now, of course, to multiply fractions together, we're going to do 7 times 7, which is 49, times 1, which is just 49. Right? In the denominator, we're going to have 1 times 5, which is 5, times 1, which is 5. So we have 49/5. Now we want to think about simplifying that. Well, 5 goes into 49 9 times. That gives me 45. I have a remainder of 4, so my volume is 9 4/5. But 9 4/5 what? Well, the normal linear measurements, the length measurements here, are in inches. So if I have an inch times an inch times an inch, then I have a cubic inch. So we'll have 9 4/5 cubic inches. and that's it, right? Now again, this is a little bit tricky because you've got to really convert, you don't absolutely have to, but it's pretty brutal if you don't. You have to convert those fractions, those mixed numbers, into improper fractions so you can then find their product and do a little cross-canceling and stuff like that. Let's do one more that's got some fraction work in it. This one's kind of cool. Exercise number 4. If a cube has edge lengths of 1/2 inch each, how many of these cubes would fit inside of a cube whose edge lengths are 1 inch each? Explain. All right, I want you to play around with this problem on your own. Pause the video now and take up to like maybe 5 minutes with it. All right, well, this is all about volume, right? How many of one thing fits inside of another thing is really all about volume because it's about taking up 3-dimensional space. Now, keep in mind, what I'm really asking is, if I have, a unit cube, right? So if I have a cube that is 1 centimeter by 1 centimeter by 1 centimeter, how many of these cubes will fit inside of this one? Well, this one's simple enough, right? It's got a volume equal to 1 cubic centimeter. I mean, that's literally, by definition, what this thing has. So the question is, what is this volume? Well, this volume can be found, obviously, by doing 1/2 times 1/2 times 1/2. Now, you need to be very, very careful here. It'd be really easy to think that this was 1/6 or 3/2 or something like that. But, of course, the way that we multiply fractions is by multiplying the tops, and there's no cross-canceling that can occur here. 1 times 1 times 1 is 1. And then multiplying the bottoms, 2 times 2 is 4. 4 times 2 is 8. So we get 8, and therefore the volume of that particular cube is 1/8 cubic centimeter. Oh, not centimeters, it's inches. All of this is inches. Yeah. And there's inches down here. It doesn't really matter whether we're using inches or centimeters, although we really should be consistent one way or another. And the problem does talk about inches, not centimeters. All right, so we have 1/8 cubic inch. So how many of these can fit into this? Well, again, as long as you understand the whole idea of fractions, there should be 8 of these that fit in here, right? So 8 will fit in, right? That's just the whole point, right? I mean, if I took this thing and I cut it up into 8 equal portions, each one of them would have a volume of 1/8 cubic inch, given that this thing has, I still have centimeters there, given that this thing has a volume of 1 cubic inch, this has a volume of 1/8 cubic inch, that means 8 of them will fit in. Now, one of the cool things is you can really visualize this quite easy, okay? So if I actually took this thing, right, and I kind of blew it up so that it was 1 inch by 1 inch by 1 inch, and then I kind of marked off the 1/2 inch marks on every single edge, you can really see the 8 of these things that fit into this thing, right? There's like that 1, right? There it is, same thing. And then I have 1, 2, 3, 4 of them, and then another 4 on the bottom, 8 total ones that will fit in. But that is a classic volume question. You know, if I know the volume of one object, and I know the volume of another, and I want to know how many of these fit into this one, well, then I just divide, if you will, right? I just think about how many of these will divide into this, and in this case, there are 8 of them. All right, let's wrap this up. So finding the volume of right rectangular prisms, i.e. boxes, is something that you've been doing for a while, but this may be the first course where you actually have to deal with it with fractional side lengths, right? You know, in previous courses, Math 5, Math 4, you may have calculated these volumes, but the side, you know, the edge lengths were all like whole numbers, 2 inches, 5 inches, 10 inches, whatever, right? Now you'll have to also deal with their volumes when the edge lengths are fractional in nature. And again, it's messy, but you know how to multiply fractions, and given that the volume formula is simply length times width times height, you just got to have faith in yourself that you can multiply the fractions and you'll get the proper volume. All right, we'll be doing a little bit more volume work a little bit later on in the unit. For now, I just want to thank you for joining me for another NGen Math 6 video by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.